normal T has never been like, never done it for me. Alright, let's get going. Okay. Quick check that you guys can see Krita. You can see me drawing. And I am a little bit in the way, so we'll go here. Thanks, Ash. I worked really hard on it. So I'm super glad to hear that you like it. Alright, let's get started. Ooh. To find a good place for my mouse. And... Alright, chat, so let's talk about cars. Today, I want to talk about the ways that your car has to sort of orchestrate all its wheels in conjunction with each other in order to drive properly, because there's actually a lot that goes into it. So, just for reference, before we start, I'm gonna make all of my examples about a car with rear-wheel drive. But everything that I'm going to talk about is applicable to all cars, right? So rear-wheel drive is like you have your engine in the front, right? And it's going to send its power all the way to the back to an axle that has both the rear wheels. And I'm just using this because I think it's an easier example for some of the things I want to talk about. But like I said, everything I'm going to talk about today applies to all of your cars. It applies to them regardless of what form of drive they have. Okay, cool, so let's go. Alright, to start with, we're going to start with some basics. And it's going to start really boring, but I promise you, it will get more and more interesting, and at the end we'll be talking about some really cool stuff. Okay, so I want you to imagine a wheel of some radius that gives it circumference c, which I know this sounds a lot like it's gonna turn into math, but I'm gonna really avoid doing math. So it's just this beginning part. So obviously with circumference c, if it goes all the way around is the length c, when you rotate this wheel once and you make one rotation, it's gonna cover c distance, right? Pretty simple stuff, but just in case anyone's not necessarily up with the program, this is how wheels work, assuming they don't spin. So if we have one wheel that spins once with circumference c, it's going to cover c distance. And now what I want you to do is I want you to imagine a second wheel, also circumference c, that is linked with the first one, so that when the first one spins, so does the second. If the first one does one rotation, the second one does one rotation. And so of course that means when the first one rotates once and the second one rotates once, the second one also covers distance c, right? And it sounds stupid because I'm just repeating myself, but it's gonna make sense when I'm talking about this in a little bit. Okay, so if you imagine a dumbbell, right? And you go to the gym and you have a dumbbell, which is basically what these two wheels are. It's two wheels mounted on the same axle, so they spin together. If you roll a dumbbell across the gym floor, you'll notice that your dumbbell always rolls straight. And it's because of what we just talked about. I drew this probably a little too small, or a little too large. Because of what we just talked about, where the whole dumbbell makes sure that both sides spin at the same rate. So one rotation on the left is one rotation on the right. And that means if the left side covers C, the right side also has to cover C. It means it has to go straight. It can't turn because in order for it to turn, one side has to go a longer distance than the other, right? So for it to turn, this right side goes a tiny distance, and this left side goes a long distance. So they're mismatched. That is why your dumbbell's gonna roll straight. Alright? No quiz, Ash. No quiz. You can just, if you just want to zone out, you can zone out. I am just here to yap about engineering because I think it's cool. Alright. So we have established that, you know, with this situation where we have two wheels linked like this, they can only roll straight. The only way that it would ever turn is if one of them is slipping. Of course, when you're driving your car, you don't want your tires slipping. So cars, we definitely all want to avoid any situation of slipping. So slipping is bad, does a tremendous amount of damage to your tires, and it can do a lot of damage to your drivetrain too. But anyway, so with the dumbbell model, we can't turn. Alright, so how do we make a car able to turn, right? In order to make it turn, we need to deal with this problem where one wheel covers more distance than the other. So how do we deal with that? There's a couple of ideas, right? I mean, the first possible option is what we do is we can make one wheel bigger than the other. And so with our larger wheel, of course, we're going to cover a longer distance with one rotation. And with our smaller wheel, we're going to cover a shorter distance. And that's going to enable us to have that turning path with the long wheel, the larger wheel going the long distance, and the smaller wheel going a short distance. And so it sounds really silly, right? Because you obviously don't see cars with like one wheel bigger than the other. Why do you have dumbbells on your desk, guy? Alright, but anyway. So if we think of this sort of same model with the dumbbells, but we instead place them where one wheel is bigger than the other, right? I like to think of it as sort of an ice cream cone, right? With one small and one big. And what happens, your ice cream cone looks like this. There's like a center turning point, and your smaller section traces out a tiny circle, and your larger section traces out a bigger circle. Right? And like I said, you never see a car like this. Of course, you don't see cars with these ice cream cone wheels, but it's sort of an interesting idea, and there's some application to this idea later on. I just want you to remember this sort of model, the sort of ice cream cone wheel model. So yeah. And who knows, maybe in the future we'll have it. But that'll come, like I said, we'll come sort of back to this model later in the talk. And it's later on down the road when we talk about trains. We'll also sort of talk about this too. Just keep this idea in the back of your head. So anyway, we can't have cars with one wheel bigger than the other unless we wanted a car that only turned. So that's not how we deal with it in cars. So how do we deal with it on cars? On cars, what we do is we use this device called a differential, right? So when you're talking about our rear-wheel drive car, we had an engine, sent power backwards to the rear axle, that went to both wheels. So what the differential does is a box that goes here, where that main drive shaft connects with the rear axle. And what it does is it routes different amounts of energy to each wheel. So disclaimer, I said energy. Energy is a physics term with a very physical definition. What I'm talking about is definitely not matching the physical definition of energy, but I think that's the most natural word for me to use here. So what the differential does, like I said, is it routes energy to the different wheels at different amounts. And how it routes the energy is it sends more energy to the side that has less resistance. So if you think of the turning idea, right? If we're turning to the right, this wheel goes further, this wheel wants to go further, and this wheel wants to go shorter. So in that sense, since this wheel on the right wants to go shorter, it has more resistance. And the wheel on the left has less resistance. So because it has less resistance, we end up with a lot of energy getting routed from the differential to the left wheel, and we end up with just a tiny bit of energy getting routed from the differential to the right wheel. Like I said, energy is not necessarily the most precise term, but I think it's a very natural way to think of it. So, like I said, the differential routes the energy towards the side with less resistance, and that helps us to make one tire spin more times than the other. But there's some problems with this. So if you've ever gotten your car stuck, right? If you've gotten your car stuck in mud or on ice, or there's just some weird terrain so one of your wheels doesn't make contact, you'll notice that your car is stuck, and when you hit the gas, only that one wheel spins, right? So we've got our car, our engine that supplies energy back, differential, right? And if, say, this tire does not make good contact, or it does not have traction for some reason, you're going to notice that your car doesn't move because only this tire spins. And that's because since that tire is not getting any traction, it obviously is going to have very little resistance. So basically all the energy coming from the engine is going to route to this tire. And only that one tire is going to spin. So that is why if you have a car made to go off-roading, you might recognize a button that looks like this. And this button locks your differential. So it basically makes your differential stop doing what differentials do, and it makes these tires spin at the same time, right? So however much the right tire spins, the left tire has to spin also when you press this button. So it locks your differential stops doing differential things, and it spins your tires at the same rate. Now, what happens if you lock your differential and then you try and turn? The answer is bad things happen. So, like I said, of course, because your tires are trying to cover the same distance since they're turning the same amount, but they're being forced to cover different distances, they're gonna slip a lot, which is going to shred them, and you're gonna lose a ton of tread really quickly. But also, all that resistance they're facing that they don't normally do, all that stress of forcing them to slip, is actually going straight to your drivetrain too, because your drivetrain is trying to turn them and they're resisting turning the way that they're supposed to. So what that does is that actually does pretty catastrophic damage to your drivetrain if you do that for too long. So that's why you don't just press that button all the time, of course. And if you want to know how I know about that, that's me speaking from life experience. There's definitely a time where a younger Breakabelle was driving Papa Bell's car, and she had the differential lock on without knowing it, and Papa Bell was not happy. Papa Bell was not happy with the repair costs. So, sorry Papa Bell, but that was a younger, dumber Breakabelle doing younger, dumber things. And now she knows better. And now I hope you guys also will pay attention, because if there's a little light on in your car that shows the differential lock, you should probably make sure not to do any turns. You should probably just turn it off. You should only really use this if you're in some condition where you're gonna slip, like you're off-roading or whatnot. So yeah, that's differentials. I think differentials are a pretty neat concept. I was really contemplating how to draw them, and I realized that there is like no good way for me to draw them. So I think it's much better for me to just show you a video. Alright, so here's a differential. You can see one wheel on one side and the other wheel on the other side. So what happens when you drive the drivetrain is this middle part spins, and that spins on both. But if you hold one of them, causing more resistance, it spins only the one that isn't getting resistance, right? So it's pretty nifty stuff. And of course, this is a very simplified model, but this is basically what's happening inside your car.
Filling in the spaces between the spokes gives steadier, more continuous action, and changing the shape gives firm, constant contact. Now we can make the gears thicker and stronger, and we have differential gears. The edges are cut so that they will fit together more smoothly and...
Okay. Anyway, back to Vita. Okay, so that was differentials. That was the first part of what I want to talk about. Now we're going to talk about another cool topic that I think is maybe less likely for people to know about, but I think this is the cooler one, so we're gonna chat about it. So if we go back to our ice cream cone model, right? Go back to the model of turning where one wheel is bigger than the other. There is some insightful information here. Okay, so you'll notice that they turn about this one point, that they are both on the same, that is on the axis of both of them. And because they're on the same axis, it's really easy to say that, oh yeah, it's just, they just happen to be on the same axis as both of them because they share an axis. So any point that's on one will be on the axis of both. But this is actually true of all wheel systems, because if you have a rigid object that is turning about, that is turning really roughly, right? Going from box like that, box like this. In order for that object to not like deform or stretch or strain or get, warped, it has to have a single point that every part of the object turns about. So we're going to draw, I might have put the point at the wrong spot. But anyway, we're going to clean this up. But the idea is, the box is turning. We're turning about this point. So that corner is going to do a circle about the point. This corner is going to do a circle about the point. This far corner is going to do a circle about the point. Right, so you can predict the path of the box by drawing these circles about the point that it's turning. Wow, I am a bad artist. Okay? Now, the insightful thing about our ice cream cone model is that what you'll see is the wheels are always have to be perpendicular with the point. So this should be like a little bit intuitive, but if you think of, say, a bike, right? You think of a bike as this long, really slender wheel, right? And the frame, goes around it that way. The bike wheel, this rear wheel on your bike, is clearly only intended to go forwards and backwards. Okay? And that might sound silly and simple, but it's really important because it informs you as to why wheels have to be oriented a certain direction when you're turning. Your bike wheel does not go left and right? It doesn't spin that way. So in order for it to go that way, there has to be slip. And of course the wheels don't want to do that. We don't like slip, right? So wheels are always trying to go one direction or along one axis. In this case, it's up and down. That is always going to be perpendicular to the point of turning, because if you're turning about a point, right? That means you have to be going along a path in a circle around that point. And that means to be going in the direction the wheel wants to go, right? Which is up and down. At this point in the circle, we need to be tangential to the circle. Okay? So that means the wheel will always, its axle will always be perpendicular to the center of the circle. All right? Now, this helps inform us of some other cool stuff. So, for example, with the bike, you have the same bike with the rear wheel. Wow, that is oddly shaped. That's the rear wheel, right? Here's the frame, here's the front. And the front wheel, when you turn, say it's angled like that, we can predict where the bike turns about, because the wheels have to be perpendicular to that point. So this bike, when the handle is turned to this angle, is going to turn about this point, right? This rear wheel is going to go, ooh, bad drawing. Rear wheel is going to go in a circle. Front wheel is going to go in a circle. And you can predict the exact motion of the bike. So how does this relate to cars? All right. So if you're like me and you think, oh, well, when we turn the car, right, when we want to turn left or right with our car, we need to turn both of the front tires. And the easiest way to do that is to do that with a linkage system, right? So if you're not familiar with a linkage system is basically a bunch of bars. Use some different colors for the ones on the sides. And they're connected by joints that allow them to, like, pivot. Right? So this would be our linkage system. It's parallel to keep the wheels parallel, right? Because your wheels are going to be like this. We have this nice little parallelogram. And then when we turn, if we have this parallelogram geometry, what we end up with is a shape that looks like this. Go back to the blue. Right. And then our wheels are now turned. That's what intuitively makes a lot of sense, to turn both wheels together, right? You make this parallelogram linkage, and that turns them both at the same time. That's how you make sure that they don't, like, be miscoordinated, right? But you might notice there's an issue. And that issue is what we talked about before, where when the car turns, every point about it needs to turn about the same point, which means there needs to be a point somewhere that is along the same axis of all these wheels. And since these wheels are parallel, there will never be a point, right? These lines will never intersect because they're parallel with each other. So you're never going to find a point. So how do we deal with this? We use what's called, oh my god, running out of space, Ackerman steering geometry, right? So Ackerman steering geometry is this similar, well, it is the same idea with the linkages, except instead of a parallelogram, what we use is a trapezoid, right? We have our trapezoid, and before you pop off like Bell, you're an idiot, our cars aren't like bow-legged, right? They don't have their wheels pointing different directions, which, would be a pretty funny thought. we of course correct for this by making these side linkages, instead of just like rectangles, we make them triangles. And wheels are attached like this. All right. So what does this do? How does this change our original issue? Well, with Ackerman steering geometry, when we turn our trapezoid, wrong layer. When we turn our trapezoid, actually end up with some really distorted turning. That comes like this. And we have our black line for the bottom part of the linkage. And we should finish these off by recreating the triangles that adjust, right? So now, when we turn, our right tire, you'll notice, has turned a lot. And our left tire has still turned, but it's turned significantly less. And so now, since it's turned less, if we draw that line for the axis, we have an intersection point. So now we do have a point that the car can turn about. All that's left is to make sure that when we design our car with this geometry, that point is in line with the rear tires. And that way, all four tires will always be perpendicular to the one point that the car needs to rotate about, and we can turn the car without slipping. Okay? I think this is super cool. I don't know about you, chat, but this is like a super interesting idea to me. And there's definitely like a lot more math that goes into calculating the exact geometries, but I'm trying not to do that math, and I don't know how to do it, to be honest. This isn't stuff that I've worked on. This is just stuff I know about. But that's Ackerman steering geometry, and this is maybe in some senses more intuitive than the differentials, but I think this is probably the coolest thing about cars, because I'm a really mechanical person, and just this visualization of changing the linkage shape to make one side turn more than the other, I think it's super cool. And this is my favorite part of what makes cars tick. So yeah, that's Ackerman steering geometry. Okay,